is the Not-Marimba. And the Not-Marimba is closer related to the marimba. Whoa, I know. So this marimba first originated in Mali in the 13th century, and the original marimbas first had, they would dig into the ground, and they would put bars over the holes that they would dig, and they would use the gourds as resonators to amplify the sound that they were making. Now, you may be wondering, oh my god, these are wood bars, and these are copper bars. What the frick? That's not the same thing. Well, actually, the marimba has what originated first, and later, the more closely related instrument, the glockenspiel, originated in Paris in 1886. And this has metal bars, so it makes a more metallic sound, and it's used to add more texture into pieces. And today, if you didn't know, these kinds of instruments can produce up to 5 octaves of sound. Okay, so believe it or not, the Not-Marimba can actually be applied to many instruments that we see today. For example, the length of the tube or note that you're going to play determines the pitch. So a longer tube is going to produce a lower pitch, while a shorter tube is going to produce a higher pitch, and that can also be seen on the marimba. See, a longer bar produces a lower pitch, and a shorter bar produces a higher pitch. See? Long tube, low pitch. As you can see, those were the same notes, but since it's a shorter tube, they had higher pitches.
So the purpose of this lab is to find the period and the velocity and to see how they're related to pitch with waves. And the other purpose for kinematics is to find the velocity of the mallet hitting the Not-Marimba.
Okay, for the procedure, you want to get your Not-Marimba, your mallets, a timer, a meter stick, and a tuner app. So first, you're going to get your meter stick, and you're going to measure each bar length and then record that and save that for later. And then you also want to put your meter stick perpendicular to the Not-Marimba so you can record your heights that you're going to be dropping them out from, which is 4 centimeters, 7 centimeters, and 16 centimeters. And then, so first, you want to get your mallet, and then you want to hold it at each height, and then release it, and then time it, so you can see how long it takes for the mallet to fall and then hit the bar. And you're going to repeat that twice so you can get a good average of each measurement. And then after you do that, you're going to divide the time it took to fall by the height to find velocity. And then after you strike each note, you're going to hold your tuner app up to the note so you can find the frequency. And then to find the period, you take the inverse of the frequency.
Wow, this is great.
This is our data. This is our data. Again. Bar length versus frequency. As you can see here, the relationship between the frequency, or the hertz, and the bar length is inversely related. If you look at the best fit line right here, you can see that the downward slope. I'm just gonna say longer bar, lower pitch.
Good. You get that?
So what the frick does that graph mean? Pretty much, a tube has a certain length, and that length will only allow a standing wave of a certain wavelength to be produced inside. Now make the tube longer. That's like the longer tube. This is a higher tube. Okay, anyways, make the tube longer, and the fundamental wave allowed in the tube will have a longer wavelength. Then also consider that wave velocity is not changing. Therefore, the tube's new frequency and pitch is going to be lower than the old tubes. Remember that frequency equals wave velocity divided by wavelength.
Okay. So one of the causes of error is the Not-Marimba is cut to incorrect lengths, so the hertz are a little bit off, which throw off all our calculations. And also, one extension we have, or improvement for the lab, would be comparing the length of the bar to the decibels it produces. So we're comparing length to loudness.
Decimals.
Decimal.
Yeah.
Do you guys hear that?